Oh, so I put this up, I think yesterday, I typed this in. This is the skills description for things that you'll have to do for the 9 and 10 test. Today we're going to just do some review problems. I'm just going to pull problems from the review. More or less, I think everything on here will be covered by doing some of these review problems. But I'm going to need help from you guys to tell me what to do on the review problems. Okay, okie dokes. Can what? Yeah. All right. So let's go, we'll start here. All right. So question 2 here that I've chosen asks you to first write down f prime of x. What does f prime of x mean? Derivative. Okay, what's the derivative of x to the 5th? Five x to the 4th, right? What are the different ways that we can ask you to, or the different symbols we can use that mean take the derivative? So if this was y equals, right? Or if we asked for like a slope function, right? That would also be a derivative. Everybody's okay? All right. Part B then says find the gradient of the tangent to the graph of y equals f of x at the point P. How do I do that? What does gradient mean again? Okay. So we have an equation that gives us slope, right? What's that equation? It's the derivative. Okay, what specific x value do we want the slope at? 2, because that's the x value from P. So what am I going to do? Plug 2 into the derivative. That's it. So that's 2 to the 4th is 16. And 5 times 16 is 80. Everybody's good? Part C says find the equation for the normal to the graph at P. Give your answer in the form ax plus by plus d equals 0, where a, b, and d are integers. What does normal mean? What? Not average. So let's say that here's our graph, and say like this is the point here, 232. That's your tangent. That one's your normal. So the normal's a line, right? You can tell it's a line because it's asking you to write it as a line. What's the slope of that normal gotta be? Nope. Nope. What? Nope. Nope. You're getting closer, though. Nope. There you go. So again, the normal should be the opposite reciprocal for the slope of the tangent, right? So if that's slope normal, that's slope tangent. So the slope of the normal is going to be -1 over the slope of the tangent. Good so far? All right, let's write an equation for our line, and then we'll rearrange that equation then to get it in the form that's asking for. So since we're given a slope and a point, let's do point slope. That's the point slope equation for a line. So what's going to go in place of y1? (32). What's going in for m? (-1 over 80). And what's going in for x1? 2. So far, so good. Okay. Now we need to get into this form, right? I'm going to worry about this part first, that a, b, and d have to be integers, and then I'm going to do the rearranging after I've got everything integral. So what do I need to do to both sides of this equation so that all my coefficients are integers? I wouldn't distribute yet, although you can, it's not wrong. I'm going to multiply both sides by -80. And then what's 80 times 32? Yuck. 2560. Everybody's good there? Last thing I got to do is just move everything onto one side, right? Does that feel okay? Could you also multiply through by -1 so all the signs are opposite? Or is x plus 80y minus 2562? Sure. Yeah, absolutely you could do that. Do you need to? No. Everybody's happy? Okay. Again, I hope that's not too bad. Okay. All right. We have y equals x cubed plus kx squared, where k is just some real number. It says then to write down dy dx. What does dy dx mean? The derivative. Great. What's the derivative then? How do I do the derivative of kx squared? 2kx, great. Is everybody happy with what we did there? Again, the k looks weird. Not a big deal though, right? Okay. It then says the curve has a local minimum at the point where x is equal to 3. What does this tell me? Says, well, it doesn't tell me y is 0. It tells me that the derivative when x is equal to 3 is 0. Right? We know that the derivative is 0 at any extrema, maximums or minimums, absolutes or locals. Everybody's good? Actually, I shouldn't say that for absolutes. If it's a closed interval, that may not be true. On an open interval, the derivative is 0 at all extrema. All right. So for part B, what are we going to do? Well, I know 0 is equal to 3 times 3 squared plus 2k times 3. Everybody's okay with that? So we have 27 plus 6k. I divide or subtract the 27 over and then divide by 6. And I can reduce that to be negative 9 over 2 is my k. Sound good? It then asks me to find the value of y at this local minimum. How do I do that? Okay, what am I plugging back in? Good, yeah, very good. So we're going to plug 3 in for x. And we're going to plug negative 9 over 2 in for k. Oops. Think that'll do it? Everybody good there? Yeah or no? Is this okay so far? Going slow enough? Explaining enough as to what we need to be realizing or what the stuff means and what that means for us to do? Do this one. Okay. Part A asks for the derivative of this function, 3x cubed minus 7x plus 4 over x plus 10 on the closed interval from negative 5 to 5, provided that x is not 0. What's the derivative here?
Minus squared minus 7 minus 4x.
Great. So again, to do that, what Diego did is he thought of 4 over x as 4x to the negative 1, and then used that same power rule for derivatives. Okay. So if we're looking for then the local maximums and minimums, what are we going to do with this? Is it okay? So if we're looking for the minimums and maximums, or local minimums and maximum for this, what do? We set the derivative equal to 0, and then we'll solve for the x. We'll do that via graphing. Now, again, to do this, if I'm doing this on my calculator, what I would do is I would not trust myself to do the derivative by hand, right? Because you could make a mistake, and then all your answers for B and C will be wrong. Do you remember how to type the derivative of f of x into our calculator? Math? Yeah, that's option 8. Then what do I fill in here? X to there. What goes in the parentheses? Y1, the equation that we typed in above. And then what goes over here where x equals? X. Good. So I'm going to turn this one off because I don't really care about the graph of that. I'm going to set my x min and x max to -5 to 5 because I don't care about x's other than that. And I don't know what's going on with the y's, but I'm just going to go -10 to 10 or something. Oops. Okay, so we see 2 solutions, right? Second trace, and I want the 0 command. So that one and there sound good. So we have x equals -1.7, well, -1.08. I'm going to round to 3 sig figs. And then the other one is and then we have positive 1.08. How can I tell which one is the local min and which one is the local max? Yeah, so I'm going to draw like a sign diagram. So look at, before I get to -1.8, my derivative is positive. Between -108 and positive 108, it's negative. And then after positive 108, it's positive again, right? So if I look here at the first, we're going increasing because the derivative is positive, and then changing to decreasing because the derivative goes negative. That's a local max. The other one, we start decreasing until we get to 108, and we change to increasing. That's going to be a local min. Everybody's cool as to how I was able to tell which one was which? Okay. And then my last piece then says it wants the actual coordinates where those maximum and minima are occurring. So my local min is going to be 1.08 comma f of 1.08. And my local max is going to be -1.08 comma f of -1.08. And again, I'm doing let my calculator do like all the heavy lifting for me. To do f of 1.08, vars, y vars function 1.08, and then to get -1.08, well, there we go. Everybody cool with what I did there? Again, you could type it in by hand into the formula, but like, why? Right? Like just another opportunity to make some typing error. Does that feel okay there on this one? So what we do is we look at these. So the graph starts out increasing because the derivative is positive, and then changes to decreasing because the derivative becomes negative. That's what a maximum looks like, right? Versus here where we start out decreasing and we change to increasing, that's what a minimum is going to look like. So again, I think about it in my head. And if we go back here, Gavin, and I change this to graph just the f of x that we started with, I should see a maximum here at positive 1.08, or I'm sorry, negative 1.08. And then if I zoomed in down far enough, I'm going to see the minimum way down there, but apparently it's like a million years down there, it looks like. I don't even know where it's at. Anyways, you get the idea, right? Maybe it's like way up high somewhere. We have that asymptote there. Let's try one more. There it is. Right? Okay. Does that one feel okay there? So again, find the derivative, right? And we talked about whether you want to call that dy dx or f prime of x or s for a slope function or whatever. We'll talk about units here in a second. Value of a derivative at a given x value. We did that like 3 times, right? You know, we did it. We talked about it here. We talked about it here, right? We're just plugging the x into the derivative. That's pretty easy. Write the equation for a line tangent and line normal. Again, if you can do one, you can do the other, right? The process is the same, just the way you find the slope for the normal is the negative reciprocal for that of the tangent. And the slope from the tangent just comes from the derivative, right? Whatever you plug, whatever x you plug into that. So we found the stationary points. That's what we did right here for this last one. Our stationary points were negative 1.08 and positive 1.08. Those are the values where the derivative is 0. We did a first derivative test here, is what we just did to classify those stationary points. That's how we were able to figure out negative 1.08 and positive 1.08 were local max and local min specifically. The second derivative test, if we wanted to do that, what we would want is the second derivative, or the value of the second derivative at negative 1.08 and positive 1.08. So to do that, if I wanted to do it that way, which you don't have to, what I would do is on my calculator, I'm going to do math. What do I want to do here? I think probably these, can I do a second derivative without doing, I don't think I can. I think I got to do this. So I'm going to type my first derivative that we found by hand in. And then I'm going to do math and derive. And I'm going to do y3. That's where I typed in my first derivative. And I'll do that at negative 1.08. And then if I do the same thing with positive 1.08, So since this is less than 0, that tells me that this is a local max. And since that's greater than 0, that tells me it's a local min. So the second derivative test says, okay, if we have some x value where the derivative is equal to 0, if I take that same x value and I plug it into the second derivative, if that value in the second derivative is negative, it's a max. If it's positive, it's a min. So it's the opposite of kind of what you'd expect, right? But that's the second derivative test. And you can use that as well, interchangeably with the first derivative test. Is that okay? All right. And then we have optimization problems, right? Oh, we did first derivative to tell where the function is increasing or decreasing, right? We did that already when we drew that sine diagram. So we're increasing from negative infinity, well, I should say from -5 up to -108, and then from 108 to +5. Again, why is it 5 and not infinity? It's just because of the function is only defined from -5 to 5. And then it's decreasing from -108 to +108. Right? So let's do some optimization problems here, yeah? All right. Okay. All right, a lobster trap is made in the shape of a half cylinder. It is constructed from a steel frame with netting pulled tightly around it. You guys ever seen a lobster trap before? You watch like the deep sea fisherman reality TV shows or whatever. The steel frame consists of a rectangular base and then 2 semicircular ends and 2 further support rods. So you have that rectangular base down there, a circle, and then they have these 2 support rods there. The semicircular ends each have radius r, and the support rods each have length L. So that length L is the same as the width of the rectangle, as well as the length of these support rods from the picture. Can you see that? Let T be the total length of steel used in the frame of the lobster trap. So part A says write down an expression for T in terms of R, L, and pi. Okay. So what is that length? R. And then what's this one? L. And what's this one? Okay. And then what's this one? Okay. And what's this one? Still L again. And then this one. And then we have this one. What's that? What? 1/2 2 pi r, right? Because it's half the perimeter. And then the same thing for that one. So what do we got here? We got 4r plus 4l plus 2 pi r. That look good? Okay. It says write down an equation for the volume of the lobster trap in terms of r, l, and pi. Yep.
Like all those equations, like
I'm sorry, what?
for like the Bermuda equations and stuff, you get those.
I would, yeah, I think that if you needed to use it, I gave it to you. Let's double check real quick. There's a bunch of stuff on your equation sheet here. Let's look. Now, I don't see anything on the list, but the good news is that you don't, if you need it, I gave it to you in the problem. So you don't have to memorize any of these geometry formulas, although shame on you for not remembering the perimeter of a circle. Okay. Volume. So what's the volume of a cylinder? What's that formula?
Minus squared times.
Or H, yeah, we usually call it H, but that's fine. It's gonna, so it's, but here we don't have a full cylinder, right? How much of a cylinder do we have? Half. So half pi r squared, and then L is the height, right? And then I guess it tells us that the volume is 0.75, so Ms. Kroll is like on it today. We've been real excited. Nah, it's all right. None of you guys really want that, do you? You do. Okay. All right. Here's a hard question. It says, show that t is equal to 2 pi plus 4 quantity times r plus 6 over pi r squared. So if you look at this equation for t, what do you notice is not in it? What letter? L, right? The equation we had before had an L in there. Guess what I'm going to do as my first order of business? I'm going to use this equation to get L by itself and then drop it into the other one. Good with that plan? Okay. So 0.75 is 3/4. So if I multiply both sides by 2, that'll get rid of the 1/2, right? And then if I divide both sides by pi r squared, I have that. So far, so good. When I multiply the 4 with the 3/2, I get that. And if I take a look now, I notice that this part I got, right? So somehow this piece has to come from that other 2 things, right? So tells me I got to take an r out of both of these things. And hey, that'll do, Bob. Is that okay? All right. Part D says find dTdr. Notice that to do this problem, I do not need to have done part C, right? Because part C, I have the thing I need to take the derivative of already. Even if I wasn't able to show it, I still got what I need. Oops. So, what am I going to... The way this is currently written, am I ready to take the derivative of it? Probably not. What should I do? Okay, distribute. That's fine. And then what am I going to do with that last part, the 6 over pi r squared? I got to do that. Because I got that variable in the denominator. Now, when I take the derivative, what's the derivative of 2 pi r? 2 pi. What's the derivative of 4r? 4. What's the derivative of 6 over pi times r to the negative 2? Fantastic. Everybody happy there? So the next statement says the lobster trap is designed so that the length of steel used in the frame is minimized. That's T is what they're talking about. So to minimize T, what do I need to do? I need to solve dTdr, the derivative of T, equal to 0. What am I going to do that? I'm going to graph it on my calculator. You got it, dude. And again, if you weren't confident that you did the derivative correctly, what should you do? Use the equation for T. Let's do that just in case. I mean, I know we did it correctly, but like, it's just a good habit. Like, don't take any unnecessary risks. You have this fancy calculator that you can use all the time throughout, no matter when you're at. Everybody's okay here? Now, when I think about R, that's the length for the radius of that piece. So I know that's a length that can't be negative. And this is in terms of meters. So I'm guessing probably, well, in the next problem it says 0.79. So I think 1 meter is probably enough. And then T is going to be a length. So again, you know, that's probably good enough there. Oops, and I probably wanted to give me some negative on that. Yeah. Ah! Okay. So if I look at my graph here, There's my x-intercept. So I get R is 0.1 or 0.719. And if I draw my sign diagram, we're negative before that and positive after that. So that means that we were a local min. This is the show part, right? Well, actually, I probably need the whole thing. Is that okay? F then says, calculate the value of L for which T is minimum. So I need an equation with just R and L in it. I'm going to use that one. And then in place of the R, I'm going to use that minimum value for R. So I get 0.924. And then the last piece then is to find my value for T. So here I'm going to use that equation, and I have values for R and L now, so I'm just going to plug those in. That was 2 pi R. Does that feel okay to use, guys? Again, for the most part, like, pretty doable, right? Like, not overly complicated. Like, the mathematics pieces are simple to do. Understanding what to do and where to get the pieces that you need, that's the hard part, right? But the actual execution is usually you're just plugging a number in or like solving for a value, like nothing like tremendously complicated. Let's see. Let's do another one of these. Okay. Consider the function f of x equals 3/4 x to the fourth minus x cubed minus 9x squared plus 20. Find f of -2. How do I do that? Yeah, just plug -2 in for x. So I'm going to use my calculator to do this, because I suspect on this multi-part problem, I'm probably going to have to use this formula a couple of times. So I'm just going to get it into my calculator now. So I don't have to deal with it later. And I'm going to leave the derivative in there, right? Because I probably want that at some point. So I do that, I get 4. What's the derivative then going to be? Somebody other than Diego or Isaac. All right, Gavaroni, hit us with the derivative here for f of x.
So 3x.
Mm-hmm. Cool. Mm-hmm. Nope. The derivative of a constant is 0. So if you think about if I graphed y equals 20, that's just a straight line, right? What's the slope of a straight line? Always 0. So the derivative of a constant, always 0. But good up until there. Ugh. All right. It says the graph of the function f has a local minimum at x equals -2. What is this telling us then?
That's where the derivative equals 0.
It tells us f prime of -2 is equal to 0. Yes. Using your answer to part B, show there's a second local minimum at x equals 3. So we're going to be doing this, right? Since it says using our answer from this previous part to show, let's do that algebraically. So those are my stationary points. So I'm going to pick a test value here on either side of 3. Now, I don't care about what's happening elsewhere because it doesn't ask us, just says show that 3 is a minimum also. So if I plug in 1, I'm going to think about plugging it into here. When I plug 1 into 3x, I get a positive. When I plug 1 into x minus 3, I get negative. And when I plug 1 into x plus 2, I get positive. Positive times positive is negative. When I plug it 4 in, I get positive, positive, positive. 3 positives is a positive. So we're going decreasing, turning to increasing. That's a local min. Is everybody okay there? You could have actually plugged in 1 and 4 into the derivative and got the actual value. That would have been fine. But like, it just feels like unnecessary to me. It's like extra buttons on my calculator. If you don't have to do it, don't do it. You can if you want, though. Not wrong. Part D says sketch the graph for the function on the interval, or for x is this and y is that. Indicate on your sketch the coordinates of the y-intercept. Okay. All right, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 10, 20, 30, 40, 50, 10, 20, 30, 40. All right. I have a local maximum at x equals 0, right? Because I know that negative 2 is a local min, so I know it has to go from negative to positive on the derivative. So 0 has to be a local max. I know the 0 is at 0, 20. So I know that's happening there, right? Is everybody okay there? At negative 2, we're at a minimum. I don't know where that's going to be. It doesn't really matter. And then at 3, we're at a minimum. Other than that, it doesn't really matter. If it's just a sketch, that'll do. So it looks kind of like a W. But a W that my 4-year-old daughter would have drawn that doesn't look quite symmetric. Everybody happy with what I did there? I think the only thing they'd really care about is this. Well, this, and then those being at negative 2 and negative 3, there's a minimum. I don't think they would care about the y coordinates there. Just that there's a minimum there. Everybody's good? And again, could you have just typed this thing into your calculator and on the window, specified window, and just copied it down? Yeah, you could have. Right? Like, you have the equation for it. It's, like, not hard to do that. It says, write down the coordinates for the local maximum. Well, we did that already, right? Just 0, 20. Oh! Everybody's good with how I came up with that, though? It says let t be the tangent to the function or to the graph of the function f of x at the point 2, negative 12. Find the gradient of t. How do I find that? So I do f prime of 2. So when I plug that in, I get 6 times negative 1, that's negative 6, times 4, negative 24. Or you could type in your calculator. That's fine as well, right? Like, definitely okay to do that. And again, to get that into our calculator, did I put that in already? Yeah, good, okay. So I would do math, command 8, derivative of y1 when x is equal to 2. Now, keep in mind, I got a crazy decimal here. Your calculator's not actually computing the derivatives and plugging those things in. It's doing like an approximation. So like, if you get a crazy looking decimal, it might not actually really be a crazy decimal. It's probably a whole number. You know what I'm saying? So this level of calculator can't do this exactly. It's just going to do an approximation. And I'm not positive how it's doing the approximation. I think it probably is using the graph. Okay. The last part here, the line L passes through the point 2, negative 12 and is perpendicular to T. L has the equation of x plus by plus c, where b and c are integers. Find the gradient of L. What's that got to be? One over 24, right? So the negative of a negative, that's positive. Okay? And then to find the values of B and C, let's do this. Multiply both sides by 24. Y. And then to get it all onto one side, what's my problem though? There's one little problem with the way I've written things. X needs to be positive, right? So B is negative 24 and C is negative 290. Now, if that X had a coefficient there, if we're allowed a coefficient, then my previous answer would have been fine. Right? But there's no coefficient on the X, so I can't have like a negative 1 there. It has to be positive 1, which is really kind of a lousy way of them framing that question. But, well, there it is. How'd you guys feel on that? It's all right. Again, for the most part, the actual like meat and potatoes of doing the problem, not that much to do, right? Knowing what to do and where to go to get the equation you need or find the number you need or whatever, that is often the tricky piece. Sure. All right. You guys try this one for me. And then we'll go through it, and that'll be the last thing we do today. Actually, I lied. I don't want to do this one. Let's do this one. Just as many parts, but this is a better one. Go give it a shot, guys. Get your stuff out. You're looking for places where the function would become undefined. So looking at a graph would be nice. The problem is that there's a B here, so you can't just type it in your calculator all willy-nilly. But this would have been a good hint. about the vertical asymptote. Just x equals 0, guys.
Okay. Only I didn't think to be that.
No, it should absolutely be that easy. Yeah, hence a vertical asymptote. It's the y-axis, right? X equals 0. It's okay. This is why we're doing them, right? Get you guys thinking. Oh, sorry. Yeah. So, Gavin, like if we have something like this and say this is our point, that's the tangent. So just, it's a line that has the same slope as the function at that point. And it passes through that point. What you'd show is that we know that 3 is equal to b minus 2, 1 to the negative 3. So that's my x, and that's my g prime of 1. And that allowed me to solve for b. What are you missing to find the equation of t? What do you still need? Well, you don't have the y-coordinate of the point that it's passing through, right? You have the slope of the line. You have the x-coordinate where it's passing through, but you don't have the y-coordinate on the function. So you need to do like g of 1. So b is 5 then, right? So that's 3. So then we can say y minus 3 equals m times x minus 1. And it doesn't tell you the form of the equation you need to write, so I would stop right there with my point slope and go, good enough. You weren't specific. Tell me mx plus b or a plus by plus d equals 0, or, like dealer's choice. That's my choice because I'm done already. Now, E you should be able to do no problem, right? plug that bad boy in your calculator and just find the zeros. It's the original problem, just the g of x, right? Because that's what it's asking for. I don't know what they are, but like, and I might have even, it might have been great even to have read question FI before I started doing part E, since it gives you a window to view the graph on, right? You see that? So if you're not sure, like, okay, I need to, well, how am I going to find this thing? Maybe read ahead a little bit and see if it gives you a viewing window, like this problem did. You guys see that in FI? I'm just going to add the 3 over and type it in like that. You know what I mean?
Yeah, you're right. You can do that. Even if you like distribute.
Yeah, you can certainly do that. Yeah, absolutely. Yeah, it's one of those things, it's like I don't want to make any mistakes. I'm just going to do it the simplest way possible and let the calculator sort it out. So there's my goofball function. There's my tangent right there to 1, 3. Yeah, I mean, it was all basically calculator and then just write down what you see. It says to make sure that you clearly indicate your answer for part E, so it wants you to like make sure that this point is on there, labeled or whatever, but like, whoop-de-doo-doo. That's not much. And then it says, using your GDC, find the coordinates for local minimum. That's right there, right? Whatever that point is. It's probably not quite 1, but pretty close. You could do it on the calculator from the function. You wouldn't necessarily have to go and use the derivative, although you could. Although I think that would be a little bit harder than it needed to be. So on 0 to 5, where is g of x increasing? Well, it's from the x coordinate of the minimum all the way up to 5, right? I can just look at the graph and see it. Don't even need to use the derivative if I don't want to. Does that feel okay? So you guys feel better? Yeah. I mean, like, still do some optimization practice. That tends to be the hardest thing. You know, looking at 17 might be a good one to look at. 18 and 19, I think, are harder than you need to worry about. But, you know, should be okay. You know what I mean? I don't think the test is too bad. I don't think it's any harder than the stuff that we did here today. Oh, hey, here's the thing. We forgot to talk about one other thing, right? There was one thing in here we said we'd get to, we didn't ever get to. Units for the derivative. So if my function is like c of x, where c of x is dollars and x is like units, well, let's not say units, let's say things. So it's like a cost function, like how much does it cost to produce 10 things? If I do the derivative, what's the unit here going to be? Yeah, very good. Dollars per thing. Right? Where the unit of the x is going to be the per on the y. But if I did a second derivative then, what's the unit going to be there? Dollars per thing or dollars per thing squared? Yep. That's good. Does that feel okay? All right. That's the gist of it. That feels like enough, right? Yeah. Keep it simple, Mr. Kulik. All right, you guys